Hey everyone, welcome. So what we're going to do is today is day 25. We're going to be talking about properties of light. Specifically, this is our very last day together with this unit. And what I mean by that is that we're just going to talk about, is light a wave? How does light behave? What exactly does light do? How does light interact with you and I in just like our everyday thing? So homework wise, you know that due at the end of the week, you have these 5 EMR practice problems, and then due next time, you don't have anything. I'm not going to be assigning anything of the sort quite just yet. So that's our main idea. So let's kind of talk about what is light in general and how does light behave. The first thing that you need to remember is that light is an electromagnetic wave, meaning it always travels at the exact same speed dependent on the medium. But in a medium, in reality, there's 4 different ways in which a wave can take. As I said, if I just go and I hit a specific medium, that wave travels through the medium, but things happen whenever that wave is actually traveling. The first one is going to be a reflection. And a reflection is just a wave that comes through and bounces off of something and then comes back at it. So the best way that I always go and I like to represent reflections are echoes. If you go and you yell inside of a room and it just goes and it echoes throughout the entire thing, you're hearing yourself through a reflection of that wave. That's the very first way in which a wave can act through a medium. The second one is called refraction. And refraction is whenever a wave bends, whenever it passes through an object or like through a material. So the really great ways in which I know how to represent refraction are if you've ever seen like lenses like this, or also another really great way to represent refraction is that if you've ever been to like the pool and you go underwater so much and then you open your eyes or you have goggles on or something and then you look upwards, the images above the water of the pool look so much different than the images below the water of the pool. Or you'll see a lot of the time of like different videos and stuff like that of someone like taking a glass and putting a straw in it and then pouring water and the straw bends. All of this is different types of refraction. Until finally we get diffraction, and diffraction is whenever a wave bends around being the key term here, or just around an object. Now, you might think to yourself, okay, that's really hard to kind of like think about just using light, because light by itself, it really is difficult for it. But the best way that I know how to represent diffraction is think about sound. Instead of talking about light, think about how like sound. If I'm way off in the distance and I yell out your name, you can hear me even if you cannot see me. That's a term and that's a way to represent diffraction. Again, as I'm going and as I'm moving, then that wave bends around an object, and it really does take a slow wave. So you don't see diffraction much in light, but that is one of our 3. And then finally, the very last one is absorption. Absorption, again, is just whenever the wave disappears inside that medium. If it's like a soundproof room, you'll see a lot of people with like different, like jagged, almost, plates that go up, and they're made out of foam, and they look like that on the side of their room or something like that. If they're in a recording studio, that's all meant to absorb sound. So, the 4 ways in which just a wave in general can travel is going to be reflection, whenever it bounces off of something to come back. The second one is refraction, whenever it bends through an object of some sort. The third is diffraction, whenever it bends around the object instead of going straight through. Again, sound's not traveling through a wall or through your window, it's bending around. And then finally, absorption is whenever it goes and it just collapses. These main 4 ideas are important because what we are really focusing on today is we have a big question ahead of us. On your homework, it talks about photons, and photons are just particles of light. And we've been going and we've been talking about light being a photon, being a particle, and we've been talking about light being a wave. And here's my question: is light a particle or is light a wave? And this is a really like famous physics question, trying to determine exactly how we view and how we can see light. So what we are going to do is we're just going to ask ourselves, is light a particle or is light a wave? Now, What ended up happening, again, this gets a little bit into modern and kind of talking about what we talked about last time with quantized values, but there was a person named Thomas Young, this dude, even though that's a really, really young photo of him, and he came up with this idea to try and test the double slit experiment. Now, Young's double slit experiment goes like this. What he is going to do is he gets some generator of light. You now know it as like a laser, but they didn't have lasers at this point, so think of it like a flashlight, more so than anything else. He's going to take a flashlight and he is going to shine it through a just panel that has two openings, two slits, one here and one here. And then at the very, very end, he has a photoreflective screen that tracks and monitors how that light is going to act. Now, he is trying to answer this question, is light a particle or is light a wave? And in reality, there's two different setups and two different possibilities that Thomas Young could see. If light behaves as particles, what's going to end up happening is that these particles shoot through each specific opening on that screen, and then they can see that image at the end just as one point. Or, if light behaves as waves, these waves are going to come through, they are going to interfere with each other. They are going to have constructive and destructive interference, and then you are going to get this pattern of many, many, many points along this screen. Let me kind of describe this to you again, just through like videos. If you go and if you take this specific value and you just make it such that you shoot it through this screen is going to go and particles are going to come through here, and eventually you're going to be shown two separate lines on the back side of whatever you're trying to read. Or if these lights behave as waves and wave functions come through, then this is going to be constructive interference along the entire thing, and you are going to have points here, 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 wherever the waves meet, and it is going to go and show you. So, here's the main idea. If light behaves as a particle, you're going to see two spots in which the light will hit that back screen. Think of it like a photograph screen. Or, if light behaves as a wave, then you're going to see many, many, many lines first on that screen. I want you to think, whenever Thomas Young went and performed his experiment, what do you think his results were? Well, his results looked like this. Meaning, it's an interference pattern. An interference pattern, again, shows you that there's points of constructive and then destructive interference in between each. Meaning that light behaves as a wave. And they thought, for the most part, this was open and done with. Thomas Young was way, way, way before, like, Max Planck or, anyone else that thought quantum. So he just shined a flashlight through and he's like, all right, light's a wave. Check, done, move on. Until, of course, Max Planck comes up and he figured out that light is quantized. Remember, that only a specific amount of energy can travel through. So what he did is that, not him precisely, but someone that he was working with, after his results came out, they went and they tested using one single electron through this double slit experiment. They're going to go and they're going to shoot one electron at a time because they thought maybe like the light particles are bouncing off of each other and they're crashing, and that's why you get a wave function. And it's really, they really didn't know. So they're like, all right, one electron at a time. Every single one, just go bounce, 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 bounce. The idea here is that they're trying to really, really think, is it going to then act like particles again? Or is it going to act as a wave function after? This is your main idea and how they're trying to represent this type of data. So they redid it, and again, they got an interference pattern. And they're like, okay, fine, light's a wave. If their main understanding, even if it's quantized, that light is a wave, that's great. But you need to understand there's a really, really big conclusion here besides just light being a wave. Think of it. They're shooting one single electron through. One singular electron through this double slit. and they're trying to see what in the world it needs in order to have this pattern. Now, the problem is this interference pattern, think about it. How many waves does it take to get an interference pattern? You have to have at least two of one wave has to crash into the other and either construct or destructively interfere using the superposition principle onto the other wave. If you're only shooting one object at a time, how in the world did one object interfere with itself? The idea here is that they agree, light's a wave, fine. But now you have one electron that literally is interfering with itself to create an interference pattern at the end of that screen. The big idea is that you can't have an interference pattern without more than one object, more than one wave. So what they did is that they said that the electron has to split then into two pieces, go through both screens at the exact same time, and then recombine at the end in order to create that interference pattern. Now, this should sound absolute bonkers to you, and it sounded bonkers to them. They're like, it's not possible for an electron to split apart, combine back again, that energy then interferes with each other, and crash into the screen at the end. It's not really feasible in physics. You can't say, oh yeah, no, absolutely, because of the interference pattern, the electron splits in half, recombines at the end, crashes into the screen, done. Come on. So what they did is that they went and they set up something, just a recorder, because they wanted to see which slit that electron went through. Or if it goes through both slits at the exact same time, then they want to see where that electron splits and where it recombines. That's the main idea here. So they repeat their experiments now with a detector in between the slits and the screen, and they're saying what happens to that electron whenever we shoot it singularly through those two slits at the same time. And what they got is they got that the results changed. The electrons then behaved as a particle once they put something in between them. The very act of looking at this particle changed the way in which it behaves. This is called the observer effect, and it's one of the most fascinating things in physics. Of you specifically looking at it changes the way in which it behaves. Now, you go and you ask Mr. Tate, all of this is confusing the heck out of me. I got that light with a flashlight is a wave. I got that even a single quanta of light, a single electron, is still a wave. But then this electron splits in half, and then it recombines, and then it acts as a particle because we're watching it, and my gosh. Yeah, it's a really, really, really big idea here, because we're saying that there's something called particle-wave duality. Basically, the end understanding is that light can behave both as a particle and a wave depending on how you treat it. So this is my definition for it. I said that light is a wave. Unless you look at it like a particle, then it's a particle, but it's also a wave. It's simple. It's fine. It's, again, one of those things in physics that's so fascinating, and we don't really have a perfect understanding of it. You in your 9th grade, it's not so much a logical conclusion. You can't think of it logically and have it end up with a correct value. It's a mathematical conclusion, and you don't have the math yet. But your main idea is that you need to treat light as both a particle and a wave. They are both, depending on how you treat it. That's the main idea with the double slit experiment. But this really does tell us a couple of things. First off, you're going and you're asking yourself, okay, Mr. Tate, the number one thing that I always go and I see is, The only notion of light that I have is through my eyes, and my eyes every single time are seeing X and Y, and my blue phone over on the side or my navy blue shirt. Like all of it is just light. And you're right. The main source and definition here is that my students really, really get confused with color a lot too, which is why I like to describe color a little bit. Color is just the wavelength of that light. It's how much energy it has, because you can solve for the frequency now, hopefully using your electromagnetic wave problems in order to solve for the energy. Different frequencies create different amounts of light, such as 400 nanometers, again, smaller wavelengths equals more energy, or 665 nanometers for red. That's the main idea. But you see color because light is called additive in physics, as opposed to in just colors like mixing in general through what you've seen in art. It's called subtractive additive. And this is the main idea, is that I have two really, really cool. This, I went and I saw, it's a prism that you go and you hang up in your window. And this shows, again, that light is additive. The very, very primary color of light is white. If you add, because sunlight is just white. If you add it all together, then you have a primary color of white light. Or this experiment is going and it's showing you the subtractive amount. Now, this experiment you can do just on your own. What you do is you grab a thing of milk, you put different types of food coloring all in it to mix. Well, don't mix, because if you mix, then it's going to mess up. But you drop different things of food coloring, all in it, and then finally you put some dish soap in the middle, and because dish soap is hydrophilic, meaning that water goes away from it, then you get these really, really cool color patterns. But again, this shows that because it was dark at the beginning, that's subtractive, as opposed to additive with what you see with just light in general. So if you want to really, really think about rainbows, stuff like that, rainbow is just sunlight, white light that's been broken down into then all of its primary colors. Roy G. Biv. That's the main idea here, and how you see color. But how you really see color is because the quantized value of that light. The color is the wavelength of that energy being reflected. So white light, sunlight, just by itself, has every single form of light in it. Again, it's additive. So whenever you go, your shirt, your whatever, has elements and has pigments specific to that quantization, meaning it only absorbs through its element. The electron then jumps to another atomic energy level, and then whenever it drops back down, it fires back this light in this color in which you're seeing. So my navy blue shirt, my blue phone, all of these are sending back energies of around, I would say, 400 nanometers? Something of the sort. That's how you go and that's how you see and interact with light. So, really in conclusion, if we want to talk about it, light's an electromagnetic wave. And we say wave, just generally because for the most part, light is a wave. Unless you go and you treat it as a single energy quanta and you observe it, in which case light's a particle, but little things. Light's a wave. And the way in which you see color is because light goes and reflects off of certain things in specific energy quanta, which you've learned last time. All of this is really, really fascinating, and most of the time now we would do a couple of labs in order to go and solidify this understanding, but this is the end of our unit. Light's it, and we need to move into thermo. So let me tell you what we are going to be doing next time. With the end of the unit, I think it's only fair that we have some sort of assessment. And an assessment does not mean a test. It does not mean a quiz. It means, think of it like a homework assignment in which I'm going to take specific questions here and there from anything we've done in this unit and throw them all together. That's what it means. So I want to go through a couple of things as to kind of how this looks. Whenever you hop on for our class, next class period, day 26, your job is to go into the quizzes section of our Canvas page. Right there in the quizzes section, I'm going to have an assignment that says Unit 7, Waves and Harmonics, done. This is assessment, probably. And with that, it's just going to have a couple of questions. You're going to have to solve some problems. It's going to look very, very similar, but nowhere near in length to the type of tests in which we've had in the past. Now, I am going to do a couple of things. Number one is that no, it is not going to be for a large amount of points. It's merely a means as for you to go and look back through the entirety of the unit and try and find items that maybe you have not quite looked at in the past or that you need to refresh, something of the sort. That's the main purpose for it. Now, I am going to go and I am going to say that unlike a normal test, you are going to be using anything at your disposal. Literally, hands up in the air, anything at your disposal. So you can have past notes in front of you, you could have homeworks in front of you, labs. You can use the videos that I've been posting on Canvas. You can go and you can text your friends and all have a group chat. Fine, don't mind. You can go into the internet. It is literally anything. There is no physical way in which you could have academic dishonesty with this assessment. There is literally anything at your disposal, except me is the one. Now, what I am going to do is that I'm going to allow you to have 3 times to submit. I don't really think infinite is quite the play here like we've been doing with our homeworks, just because the homeworks are meant for learning. It's meant to say, okay, I got this wrong. Let's go back. Let's fix it again. Here, boom, boom. And it's that process. The assessment is here going and saying, you have learned this material, but now you need to show me that you know it and that you can practice it. So I don't like one submission. That's just cruel. So I'm going to make it 3. First time, try it. See what you get. Second time, again, see what you get. Hopefully get a little bit better. Third time, done. That's the main idea because you have already learned this material. And that's it. So next time for class, and there's not going to be a new video, I'll probably post something onto our Canvas page again saying day 26, and I'm just literally going to write in there, go into the quizzes section, take the assessment, check. But these are the rules. These are the guidelines. You are more than welcome to ask me anything, but this is the idea that you are going for. But everyone, again, thank you. That's the end of our unit. I miss you all, and have a great rest of your day. See you, everyone.